3, 2, 1, go. Hello and welcome back to Calculus 1. Calculus 1, there we go. The second one, ignore the first one. So, are they gonna make it over there? The first time it cracked my, you still haven't heard my real voice. I've been just, whatever. Anyway, so this talk, this conversation or presentation, whatever, is not a lecture in the book. This is more to tie the entire chapter 3 together. We are not done with chapter 3 yet, but more stuff is coming. But the story of the tangent line is the most important thing in chapter 3 and one of the most important things of the entire Calculus 1. It's one of the focal points. Tangent line measures instantaneous rate of change at the point you are observing. So that point could be the entire year, as we've seen last time, right, for the population growth. So how many more people do we add in 2018 or 2019? So if you know that 2019 is like a snapshot in time, yes, it's a year, but we are measuring across that year how many more people are added. So the tangent line measures the change, and the tangent line measures the instantaneous change. So your speed in the car as you are driving, all of that are just values that you are getting from the tangent line calculation. So the procedure for the tangent line is you get the slope, you have the point, and just use the algebra to put the line together. The slope you will get through the first derivative. So that's that. So if I have some kind of a function and I pick a value a, there will be a tangent line at that a, and the tangent line, the slope of the tangent line measures the instantaneous change, the change at point A. So the formula for the tangent line is obviously, I should have, you know what, I'm going to change this into red. So the formula for this line is y equals m tangent x plus b. This value here is obviously value b. It has the slope of m tangent, and it goes through the point a, f of a. It's really cool. So find the tangent line for function y equals x cubed at x equals to, let's say, 2. So find the tangent line. Procedure that you are going to see now is the same procedure for every single problem. Just one single procedure. The thing that is going to differ from problem to problem is your derivative, because it will depend on the function which type of the derivative technique you have to use. So now we have that the slope of the tangent line is equal to f prime computed at 2. So as you can see in the picture, right, if this a is equal to 2, you will be computing the tangent line and that slope only occurs at a equals to 2. So the derivative, which you can do on the side, f prime of x is 3x squared. So this is equal to 3 times 2 squared, which is 12. So we found that the slope is 12. We know that x is equal to 2, and we can figure out y by plugging in f of 2, which is 8. So now I have my 3 values that I need to come up with the equation of the tangent line. Y equal mx plus b, plug in, y is 8, m is 12, x is 2, plus b, and you can calculate b. So b is equal to 8 minus 24, which is equal to negative 16. So the tangent line is given by y equals 12x minus 16, and this is the tangent line at 2, 8. Or you can just say at x equals 2, 2. Fine. It's fine. So this is the tangent line. Procedure is always the same. Get the derivative, use the derivative to calculate the slope, and then if you need to calculate the y value for the function, plug everything in the formula to come up with the slope, then use the algebra to find b. It's a longer procedure, but you know, once you get the hang of it, it's very straightforward and goes quick. All right. So when I put tangent line question mark, I'm asking to find the tangent line, all right? Find the equation of the tangent line for the function. And now I say, okay, f of x equals 2. And then later I'll need at the point x equals to something. So I need these specs to actually do the problem. So find the tangent line at, and now f of x is equal to, and we can literally put whatever we want. Well, not lns and trig, inverse trig and so on, we have to learn that, but you can put here for this function something that will be product rule, quotient rule, chain rule eventually. You can put a basic x squared. Amazing, no one is opting for that. I applaud you all. So we can place whatever we want. So let's go with sine of x squared, and I'll leave the x over here to be the square root of pi over 6. I know, weird, but we can do it, so why not? So what do I have? First order of business is to calculate the derivative so that we can calculate the slope. So the derivative, which is df dx, is equal to, and now we can say that's the derivative of sine x squared, which is cosine x squared times 2x. M tangent is equal to the derivative at a. And that's square root of pi over 6. So now I have cosine of square root of pi over 6 squared times 2 times the square root of pi over 6. So what is my slope? M tangent. M tangent is going to be, when you square pi over 6, I mean the square root, they cancel. So cosine of pi over 6 is, very good. Yeah, I gave you enough time. 3, 2, 1. Yeah, pi over 6. Wow. Root 3 over 2. Times 2 square root of pi over 6. 2 and 2 cancel. All of this goes under the same radical, becomes 3 pi over 6. Becomes square root of pi over 2. And you could leave it there, but yeah, let's leave it there. So there's my slope. Wow, amazing, right? M equals square root of pi over 2. It's going to be wonderful for later calculations. So what's the next step? Next step is to calculate y value, which is f of square root of pi over 6, which would be sine x squared. So sine square root of pi over 6 squared. The square will kill off the root. And we have just sine of pi over 6, which is equal to 1/2 radians. I mean, why did I put radians? It's just equal to 1/2. Wow. No coffee. So now I have x equals square root of pi over 6, y equals 1/2, and slope m equals square root of pi over 2. So these are the three values which I need to put together the equation of the line. So y equals mx plus b, y is 1/2, m is square root of pi over 2 times the another square root of pi over 6, that's x, plus b. 1/2 is equal to the square root of pi squared over 12 plus b. You can kick pi over 2 outside. And what's left is 1 over 3 plus b. So b is equal to 1/2 minus pi over 2. And now this is going to be root 3 over 3 because I rationalized it in my head. You can go check. Minus pi root 3 over 6. What a wonderful calculation. So we finally have a tangent line at y equals my m value, square root of pi over 2 x minus pi root 3 over 6. Cool, right? You're getting the tangent line and the linear line with only one point. That has to count for something. All right, next one. X equals 3. I've been using 3 all day long today. 3x cosine x at x equals 0. Fine, go on. What kind of derivative do we need? Product rule, right? So we have to use the product rule to solve this problem. So step number one is always to come up with a derivative. This is a product rule, so copy the first, which is 3x, times derivative of the second, which is sine x, plus copy cosine x, and then times derivative of the first, which is 3. Slope m is going to be the derivative computed at 0. What happened? Oh, it's negative over here, right? Yeah. Yes, it's negative, but it's gonna die when we put 0 in there, so plus 3. Would you expect slope to be 3 after having this trig? So now we have that. Then we calculate y value, which is f at 0, which is 0, because it's 3 times 0 times 1. So it's 0. And I have my slope is 3 and the point is 0, 0. Well, that has to be y equal 3x, right? Because the y-intercept is 0, 0. So tangent line is y equals 3x, and that's that. At x equals 0. Now, we all know what it means to have a tangent line, right? So if you are wondering if the problem you did is correct, then the function that it's given to you and the equation you calculated, the tangent line, have to, well, we say in mathematics, kiss, right? They have to touch at 0, 0 when you graph both of them in the same coordinate plane. So what we can do is we can quickly, call on Mathematica to just quickly run the test. I also want to see if it can do the tangent line from scratch. But so I hope you all installed this. You push equal twice, graph, and now we have to plug in both of these. So 3x cosine x and 3x. You push enter and you wait until it cooks it, and as you can see, there you go, right? You see it exactly. Going to enlarge this, and you see that that's 0, 0. The blue line, which is your x cosine x, and your orange line, which is the 3x, touch exactly at 0, 0. Okay, that's it. I hope you're not disappointed. So now you know that tangent line can be calculated by, you first find the derivative, you plug in the point to come up with the slope, then you plug the point in the original function to come up with y value, and then you have the slope, x value, y value, plug all of that in y equal mx plus b to get the tangent line. The problems will differ, so procedure is the same for the entire chapter 3. The problems will differ just in respect to the, what do you call it? In respect to the type of the derivative that you have to use. So is it basic, like x squared, or sine x, or you have a product rule, quotient rule, chain rule? They're all fair, right? So from here on, we still have implicit differentiation to worry about. We still have to do inverse trig. We have to do logs and logarithmic differentiation. And then eventually we have related rates. So we actually go all the way through 311. So there are 11 sections in Chapter 3 that we are covering. So I think the next one is implicit differentiation for next week. So that's going to be, again, something that you haven't done much with in the past through the courses. Bye.